Okay, in this video I'm going to be going through AS Normal Maths Paper 2. It's a Statistics and Mechanics paper. Question 1. A company manager is investigating the time taken in T minutes to complete an aptitude test. The human resources manager produced a table below of coded times in X minutes for a random sample of 30 applicants. Okay, so I'll just underline the fact that it's coded. So I've got this table here of grouped data. I've been given some summary statistics here. That's where a calculation has been worked out using the data to save you time. And we've got the sum of Fy is 355 and the sum of Fy squared is 5675. And what we need to do in part A is to use linear interpolation to estimate the median of the coded time. We have to estimate the median because this is grouped. So it's never going to be exactly what the median is because we don't have the original data. It's all been grouped. So the first thing that I need to do is to find the position of the median. So the median is known as Q2, quartile 2. And I'm going to use half n plus 1. Now you're allowed to use half n. So my answer will be based on half n plus 1. But if you use half n, you'll get a slightly different answer. But the two numbers should round to the same number when rounded to three significant figures. Right, so let's work out this position. So that's half n plus 1, n is 30, that's the total frequency. So half of 31, that gives me 15.5. So the 15.5 number is the middle number. I now need to work out which group I will find the 15.5 number. And I'm going to use cumulative frequency to help me do that. So if I work out the cumulative frequency by doing a running total as I go along here, I will find the 15.5 number in this second group here, the group that goes from 5 to 10. So let me just highlight that group there, like this. And now I can do a calculation to help me. Now the way that I do this like number line type thing. I'm going to put the time at the top and I'm going to put the positions or frequencies at the bottom. So the group that the median is in goes from the 5th time or 5 minutes to 10 minutes. The position goes from the 3rd to the 18th. So you always write down for the lowest value the cumulative frequency where the last group ends, and then the cumulative frequency where that group ends. So don't do 4 to 18, always do the previous value, so 3 to 18, because this is almost like treating it like continuous. We're continuing from one group to another. Okay, so we're trying to estimate the median, so I'll call it X here. And I know the position of that median is the 15.5 number. So let's put 15.5 here. And then what I can do is write a calculation and work it out. So for example, I can do X minus 5 and 15 minus 3, 15.5 minus 3, and then 10 minus 5 and 18 minus 3. And write that as a fraction equal to each other, or fractions equal to each other, and then solve for X. So I will write X minus 5, that's the purple one, divided by 10 minus 5, that's the green one, is equal to 15.5 minus 3, that's the purple one, divided by 18 minus 3. Okay, and I've chosen these particular parts because it means I only have X once and X is going to be positive in my working. So try and do it like that so that you don't end up, I don't know, for example, doing X minus 5 over 10 minus X. It just makes things more difficult. We want to keep just one X in our work and keep it as simple as possible. Okay, so here I'll have X minus 5 over 5, X minus 5 divided by 5. Now I'll work out what 15.5 minus 3 divided by 15 is. And I get exactly 5 over 6. So it's just rearranging it now to find X. So I'm going to times both sides by 5 So 5 over 6 times 5, and then add 5 to both sides. So I'll have x is equal to 25 over 6 plus 5, and I get an exact value of 55 over 6. So using the SD button, that is 9.1666, so on like that. We want to give the answer to 3 significant figures. So Q2, my estimate for Q2 is going to be 9.17, okay, and that's rounded to 3 significant figures. Okay, so we've done part A. Part B, we want to estimate the standard deviation of the coded times. So I'm going to use S for standard deviation because this is a sample of 30. So this is a sample. So really, when we have a sample, we should use S for the symbol for standard deviation and S squared when it's the variance, and then use sigma if it's the population, and sigma squared if it's the population variance. Now you won't lose marks if you use the incorrect symbol, but just be aware of the difference between the two. Now the standard deviation is going to be the square root of the sum of fy squared over the sum of f minus the sum of fy over the sum of f all squared. Right, so let's see what we get. So the sum of fy squared we're given is 5675. The sum of f, that's 30n, minus the sum of fy we've been given is 355. And the sum of f again is 30, and then all of that needs to be squared. So let's work that out, see what we get. And that gives me 7.00991. So always write down the answer from your calculator before rounding it. Again, to 3 significant figures, this would be 7.01. Now, if you're doing further statistics too, you are allowed to use something called the unbiased estimator to estimate the standard deviation. Okay, let's moving on to part C. So the company manager is told by the human resources manager that he subtracted 15 from each of the times and then divided by 2 to calculate the coded times. Part C, calculate an estimate for the median and standard deviation of T. So we basically need to decode these results to work out what the results were for the original data. So I'm just going to take this bit of information here and write it into a formula. So to get the coded times, x, he took the original times, he subtracted 15, and then he divided by 2. I'm going to rearrange this to make T the subject, because basically I have my x, my coded standard deviation, and I can work out the coded mean, and then I'm going to work backwards. So if I rearrange this, multiply both sides by 2, I'll get T is equal to 2x plus 15. Right, so I misread that as mean, it's actually median. Right, so what was my coded median? So basically my median, Q2, for, let's put like a little X here to say that this came from the coded data. And that value there was the 9.17. So what I do is to find the median for the original times, original data. I'm going to do 2 times by 9.17 plus 15. And that gives me 33.34. So 33.34. Let's give that to 3 significant figures. So 33.3 is the median for T. So 3.33. Sorry. Let's do. Okay. Part D. The following year, the company has 25 positions available. 25 positions available. The company manager decides not to offer a position to any applicant who takes 35 minutes or more to complete the aptitude test. The company has 60 applicants. Comment on whether or not the company's decision will result in the company being able to fill the 25 positions available from these 60 applicants. Give a reason for your answer. So we need to state yes or no, and then we need to give a reason as well. Now, we shouldn't be doing any new calculations. We should be using what we've got. Now, we've got the standard deviation for the times, and we've got the median. Now, the median is going to be useful. The median is equal to 33.3 minutes. Now, the median's the middle. So we would expect half of the applicants to take less than that time and half to take more than that time. So we'll write that down. So if we've got 60 applicants, we would expect half of those to finish in time. Okay, so we'll just write that down. We would then expect half of the 60, 30, to finish in 33.3 minutes or less. Now we can see that median time of 33.3 minutes is less than 35 minutes. So if we expect half to finish in a time less than 35 minutes, we would expect at least half to finish in less than 30 in that time, because it's a shorter time scale. We're given like longer than the median. We'd expect 30 to finish. So definitely 30 will finish in 35 minutes. Well, not definitely, but we'd expect 30. 30 is more than 25. So we'd expect them to be able to fill the post. Yeah. So we'd also say here that 30 is greater than 25. The 25 posts available would expect 30 to finish. Therefore, we would expect the 25 positions to be filled. Doesn't mean they will be, but we'd expect them to be filled. Okay, question 2. The discrete random variable x is binomially distributed where n is 30, sample size is 30, and the probability of success p is 0.28. What we need to do in part A is to calculate this probability here. Now, on our calculators, we want the probabilities in the form less than or equal to. And then when it's in that form, we can use binomial CD on our calculators. If it's not in this form, we need to change it to this form. So the first thing I'm going to do is to change this symbol here to less than or equal to, which does mean I will need to change this number here. So the probability, we've got x greater than or equal to 5, that's fine, we've got the correct symbol. So if it's less than 12, because we're talking about whole numbers, it's less than or equal to 11. So we need to think about these as whole numbers. Now I can write this as the probability of x up to 11, and then I want to subtract the probabilities that I don't want. So I do want, basically you can think of this, it's the probability of 5, 6, 7, 8, 9, 10 and 11. We're not going to calculate them separately. The probabilities up to 11, and what probabilities don't I want? I don't want the probabilities up to 4. So this is the calculation we're going to do. Okay, so using binomial CD for the first one. Now I'm going to write my decimals on the calculator correct to 4 decimal places, because I'm going to give my answer to 3 significant figures, which is basically going to be 3 decimal places for a probability question. So to 4 decimal places, the probability that x is less than or equal to 11 is 0.8939, and the probability that p is less than or that x is less than or equal to 4 is 0.0495. So always write the answers to 4 decimal places so that we can give an answer to 3 decimal places, 3 significant figures, and once we do that subtraction we get 0.844. So 3 significant figures is fine. If you want to give an answer to more significant figures or more decimal places, then you will need to make sure that the values you use here are to a greater accuracy than the one that you want to write your answer to. Okay, but I suggest 4 decimal places here, 3 significant figures for your answer. Okay, part B. Past records from a large supermarket show that 25% of people who buy eggs buy organic eggs. On one particular day, a random sample of 40 people is taken from those who had bought eggs, and 16 are found to have bought organic eggs. What we want to do is test at the 1% significance level, whether or not the proportion P of people who bought organic eggs on that day has increased. State your hypothesis clearly. So when you state your hypothesis clearly, you need to write down everything that you would do at a normal hypothesis test. So the first thing that you need to write down is what your model is. So is it binomial? Is it something else? Well, it's a binomial model because there is a sample, there's a probability of success or failure, and my sample size is 40, and my probability that it's going to be organic success is 25%, so 0.25. So always write down your model. That will be worth a mark. Next, we write down H0 and H1. Now H0 is going to be what was the historical probability of people buying eggs from the supermarket. Well, that's 0.25. What are we testing for? So it says here it had increased, so it is a one tail upper tail test. So we're looking for, has the probability or the proportion of people buying organic eggs increased? Okay, so we've got a couple of marks there already. Next part is to do a calculation. So we want to calculate the probability, because it's an upper tail test, that the number of organic eggs bought greater than or equal to 16. So this is always, this number here is what was observed. We saw 16 people buy the eggs, and we're going to work out the probability of this happening, and we'll use that to decide whether the proportion of eggs has increased. So the probability that x is greater than or equal to 16 is 1 minus the probability that x is less than or equal to 15. Remember, you always need to have less than or equal to. So that'll be 1 minus, and from my calculator, 4 decimal places is 0.9378, and so that will give me a value of 0.0262. Okay, so there's my 3 significant figures, so I did need like the 4 decimal places in this case. So this is 2.62%. That's the probability that somebody's going to come in and I would have 16 or more people come in and buy the organic eggs. Now, how does this compare to the significance level? Well, the significance level is 1%. Our calculated probability is greater than the significance level. When it's greater than the significance level, we can say that this outcome is likely. This outcome is related to H0. We always test H0. So we're going to accept H0. Or we can say that H0 is significant. Now, H0 is that the proportion of people buying these organic eggs is still 25%. and it's not changed. We need to finish with a statement in context. So just look at what's here. We can almost copy it out. Whether or not the proportion P of people who bought the organic eggs on that day has increased. So I can write, there is insufficient evidence that the proportion of people, so I'm almost just copying that sentence out, of people who bought organic eggs has increased. Who bought organic eggs has increased. Here we go. And then part C, it says state the conclusion you would have reached if a 5% significance level had been used. Now it says state, so we don't need to do any calculation. Now let's have a look. Our calculation was 2.62%, and if we had used a significance level of 5%, our calculated probability is less than the significance level. So it's like saying that H0 is unlikely. In this case, we would have rejected H0. So at 5%, we're basically saying, to have 16 or more people come in and buy organic eggs is unlikely. So I'd reject H0. And then my conclusion would be that the proportion, or there's evidence to show that the proportion of people buying organic eggs has increased. Buying organic eggs has increased. So I'd come up with a different conclusion with a different significance level. Question 3. Pete is investigating the relationship between daily rainfall, W millimeters, and daily mean pressure, P, and that's hectopascals, HPA, in Perth during 2015. He used a large data set to take a sample of size 12. He obtained the following results. So this top row here is the pressure in hectopascals, and bottom is the rainfall in millimeters. Pete drew the following scatter diagram values of W and P and calculated the quartiles. So we've got the lower, upper quartile and the median for the pressure and the daily rainfall, and we've also got this scatter diagram here. And in part A it says show that the 3 points circled on the scatter diagram are outliers. And there's a bit down here that's going to help us. I didn't see this at the bottom. An outlier is a value which is more than 1.5 times the interquartile range above Q3, or more than 1.5 times the interquartile range below Q1. So now we're going to do a calculation. We're going to first look at any outliers which are below, and the way that we do that, we just do the calculation that's given. So it's Q1 minus 1.5 times the interquartile range, IQR. That will tell us if there are any values below. So Q1, and this is for pressure, so I'll start with the pressure first. So Q1 is 1010, and I want to subtract 1.5 times the interquartile range. So that's going to be 1013.5 minus 1010, and that gives me 1004.75. So any value below that is going to be an outlier. Let's do the same for the upper end. So that's going to be Q3 plus 1.5 times the interquartile range. So that is going to be 1013.5 plus 1.5 again times by interquartile range, so 1013.5 minus 1010. If we do that calculation on our calculator, we'll get 1018.75. So in other words, if I have a pressure lower than 1004.75 or a pressure higher than 1018.75, it's going to be an outlier. Now I'm just going to mark where those points are roughly on the scatter diagram. So I can't do the 1004.75, it's off to scale, but basically any pressure greater than 1018.75, so that is going to be, let's say, about here. So any value greater than that is going to be an outlier. So these 2 points here are outliers for pressure. And those two values are 1019 and 1021, 22. So I can write down that 1019 and 1022 are pressure outliers. They just need to be outliers for one or the other, or both to be outliers. Okay, now let's look at this point. So this is going to be rainfall, and see if we get a rainfall outlier. So first bit here was for pressure. So now let's look at rainfall. So doing the same thing as I did before, if I look at Q1 29.2 minus 1.5 times the interquartile range, so that would be 50.7 minus 29.2. That will give me the lower value, and for the upper outlier, that will be 50.7 Q3 plus 1.5 times the interquartile range, 57 minus 29.2. Now if we work these out on our calculator, one will be negative 3.05, one will be 82.95. So I can't show this lower limit on my scatter diagram, it's below 0. But the 82.95, now whereabouts would that be? So I guess something like that. Okay, so that means that this point here is an outlier for rainfall. So that is the one where it has a rainfall value. It's something over 100. Let's see, 110. I don't know. We're going to have to sort of guess that value. Okay, no, we don't. Forgot it's from the table, isn't it? So this is the one. That's this one here, isn't it? Yeah. So should have been looking at the table. So this one, the 102, is an rainfall outlier. So 102 is the rainfall outlier. So we've shown that those 3 points are basically outliers. Right, part B. Describe the effect, so we don't need to do any working, just describe the effect of removing the 3 outliers on the correlation between daily rainfall and the daily mean pressure in this sample. Okay, so what I'm going to do is sort of basically delete the points or cover them up so you can see. So at the moment there seems to be a sort of negative correlation because of those points there. Let's delete those points there, so imagine they didn't exist. Now look at that scatter diagram. I don't see a correlation anymore. Those 3 points were making it look like a negative correlation. So it's gone from negative correlation to no correlation. So we'll just write that down. Part B, describe the effect. The correlation changes from negative to no correlation. And lastly, part C, John has been studying the large data set and believes that the sample Pete has taken is not random. From your knowledge of the large data set, please or explain why Pete's sample is unlikely to be a random sample. Now, the problem is most people's knowledge of the large data set isn't that great. So people are going to have problems with this. Don't just make something up. Think about what this data is about. Think about the sample size that you've got and see if you can sort of come up with a sensible conclusion based on what you know from the large data set. I do have a video on the large data set about what data is included, so if you're not sure, watch that and that will give you sort of a good summary of what's in the large data set. Now, if he's investigating this correlation between rainfall and daily mean pressure, and he's got a sample of 12 and he's doing it for the whole year, you would expect each one of these would have been taken from each month, January through to December. However, the large data set doesn't have this information for every month of the year. It's only got it for 2 years, 1987 and 2015. And for each of the years, it's only from May to October. So I'm not sure he's got these values from, but there is no data for January, February, March and April, or November and December. So we need to write that in some way, that there's some months missing from the large data set, that, you know, he wouldn't have got a sample from every month of the year. So I've just decided to put that the large data set only contains data for 6 months of the year, that's May to October. Or you can talk about the months which are missing. He's not going to get a sample of 12, he's only going to get really a sample of 6. So maybe he's used some months twice. Okay, part D. John finds that the equation of the regression line, or basically the equation of the line of best fit for the scatter diagram of W1P using all the data in a large data set, is W equals 1023 minus 0.223p. Part D. Give an interpretation of the figure negative 0.223 in this regression line. Now, giving an interpretation is not saying it's the gradient. What does it stand for? Now, the best way to do that is to look at, if you increase this value by 1, what does it do to W? And don't just use P and W, use what they stand for. So you'd write something like this. As the pressure, that's P, you put P in brackets, increases by 1 hectopascal, HPA, the rainfall decreases, because it's a negative, by 0.223 millimeters. So use the words rainfall and pressure. So rainfall, I guess I could put a little W in brackets there. That's part D. And lastly, part E. When John decided to use the regression line to estimate the daily rainfall for a day in September when the daily mean pressure is 1011 hectopascals. Part E. Using your knowledge of the large data set, comment on the reliability of John's estimate. Well, the large data set does not have data for September, or sorry, data for December. Remember, it only goes from May to October. So May to October only. Question 4. Lorna, and that is, Dawn and Sergey are sometimes late for school. The events A, D and S are as follows. A, Alona is late for school. D, Dawn is late for school. S, Sergey is late for school. You can see it on this Venn diagram here, which shows the 3 events A, D and S and the probabilities associated with each region of D. which are in here. They've given those. The constants P, Q and R each represents probabilities associated with the three separate regions outside of D. So this is P, Q and R, they're outside of D, one's outside of all three. And part A is down here. Write down two of the events, A, D and S, that are mutually exclusive. Give a reason for your answer. So mutually exclusive means the events cannot happen at the same time. That's indicated by circles which don't overlap, or if there is an overlap, that overlap contains 0. So I'd write down the events A and S are mutually exclusive since they don't overlap, or because they don't overlap. Spell that properly. Because they don't overlap. Or you could say that A intersect S is equal to 0. So you could say that instead, that their intersect is equal to 0. That shows that they're mutually exclusive. Part B. The probability that Sergey is late for school is 0.2. The events A and D are independent. Find the value of R. So we're going to have to do some calculations here. So if the probability Sergey is late for school is 0.2, that means that 0.05 plus Q is equal to 0.2. Taking away 0.05 from both sides, we solve for Q, and Q is going to be equal to 0.15. So we've got that. Then we're going to use the other bit of information here, that A and D, the events A and D are independent, which means if we multiply A and D together, we get the value of the overlap. So A and D multiply together, so that's basically 0.1 times plus P, that's A, so 0.1 plus P, or P plus 0.1, A times by D. Now our probability of D, that's going to be what all three of these add up together. So we've got 0.2, so 0.25. I'd actually write 0.1 plus 0.1 plus 0.05. And those two multiply together, so the probability of A times by the probability of D is equal to their intersect, that overlap, which is 0.1. So let's simplify this equation here so we can solve it. So I can write that as 0.25 times by P plus 0.1 is equal to 0.1. Divide both sides by 0.25, so I'll have P plus 0.1 is equal to 0.1 divided by 0.25, and then add 0.1 to both sides allows me to calculate P, and that gives me a value of 0.3, or 3/10. Now if you get decimal answers, ideally you want to give those answers as exact fractions if possible. In this case it's not a problem. Right, part B. Oh, we haven't finished part B yet. We found Q, we found P. We need to use all of that to find R. So actually what I'm going to do on my Venn diagram is write down those values. So let's stick 0.3 here. Let's stick 0.15 here. The other rule for probabilities is that the sum of all of the probabilities is equal to 1. So I know that when I add R to all the other probabilities, it's going to equal 1. Or I could say 1 minus all of this lot is equal to R. So yeah, so let's do R is equal to 1 minus what we've got here. So we've got 0.3, we got 0.1, another 0.1, we got 0.05, and we've got 0.15. Let's work that out and see what we've got left for R. And that also gives R is equal to 0.3. So let's highlight that. and let's put that on our Venn diagram. So 0.3. Okay, Dawn and Sergey's teacher believe that when Sergey is late for school, Dawn tends to be late for school. State whether or not D and S are independent, giving a reason for your answer. So we use the rule for independence for D and S. So if they are independent, the probability of D times the probability of S is going to be equal to the probability of D and S, which is 0.05. So let's do that calculation. So the probability of D is 0.25. The probability of S, so these two added together, is 0.2. Let's see what that equals. That's equal to 0.05. Now that is equal to the overlap here. So we do need to state that. So the probability of D and S is equal to the probability of D times the probability of S. Therefore, D and S are independent. And lastly, part D. Comment on the teacher's belief in the light of your answer to C. Well, if they're independent, that means that they don't affect each other. So we would expect actually that when Dawn is late, Sergey is not affected by that. So for part D, we can talk about her belief. So the teacher's belief is not correct because D and S, this is our reason, are independent. So we're not expecting that one's lateness is affecting the other. Their teacher's belief is incorrect. Question 5. A small ball is projected vertically upwards from point A, which is 19.6 meters above the ground. The ball strikes the ground for the first time 4 seconds later. The motion of the ball is modelled as that of a particle moving freely under gravity. Use the model to find the speed of the ball as it hits the ground for the first time. So whenever I do these types of questions, I like to draw out a diagram so I can see what's going on. So here's my ground here. The ball is thrown up. It then hits the ground. I know that the distance between the point where it's thrown up and the ground is 19.6 meters. So it's 19.6 meters above the ground, like this. Gravity, I'll put on that always acts downwards. So that's going to be 9.8 meters per second squared. And I know that the time it takes to do this whole up and down thing is 4 seconds. And I need to decide which direction I'm going to take as positive. Now I like to take the direction it's moving in at the start as the positive direction. You could take downwards as positive, doesn't matter, you'll get the same solution. So this is a SUVAC question, constant acceleration. I'm taking upwards as positive. Now I don't know U, the initial velocity, so we'll leave that blank. I want to find the final velocity, so I'll put a question mark by that. Now S. Now since I'm taking upwards as positive, anything above the point of projection is positive displacement. Then when I get to this point here, which is level to the point it was projected at, that would be 0 displacement. And then below that is going to be a negative displacement. So I want to know what the speed is when the displacement is negative 19.6. In other words, 19.6 meters below the point it's projected from. A is going to be negative 9.8 because remember I'm taking upwards as positive. So I'll just put an arrow here at the side so we know which direction is positive. And T is 4 seconds. So I'm looking for a SUVAC equation that uses S, V, A and T. So if you can't remember them, they're in the formula book. So we'll use S is equal to VT minus half at squared. It's very similar to that one, which is s equals ut plus half at squared. So this is to solve that equation that I'm going to use. I'll just put the values in. So I will have negative 19.6 is equal to v times t, so that's 4v, minus half at squared. So half a, now let me write this on the line below, I haven't got much space here. Let's do it down here where I've got some more space. Right, so negative 19.6, that's s, is equal to v, that's what I'm trying to find, times by t, which is 4, so 4v, minus half, times by a, which is negative 9.8, times by t squared, so 4 squared, which is 16. And all we need to do is to solve that and rearrange for v. So that will be negative 19.6 is equal to 4v, and then if I work out half, that negative half times by negative 9.8 times by 16, that gives me positive 78.4. Take away 78.4 from both sides, and then divide by 4. And I'll get v is equal to negative 24.5. Now don't panic, because we're taking upwards as positive, the velocity at this point is in the opposite direction, so we'd expect v to be negative. So we'll need to give our answer just as the velocity, so don't put the negative sign in, so 24.5 meters per second. Now you can give your answer to two significant figures, so any question that involves gravity, g, using 9.8, you can round your answer to two significant figures. That's the only time you'd want to do so, but if you stick with three significant figures, as we normally do, that won't be a problem. That will get you full marks. Okay, part B. The ball rebounds from the ground with a vertical speed of 14.7 meters per second and next comes to instantaneous rest, that means it stops, at the point B. Use the model to find the height of B above the ground. Okay, so another little diagram here. So it's hit the ground, it's bouncing up, and then it's going to come down again like this. Let's mark on what we have. So we have gravity, that always points down, 9.8. We know that it rebounds up here, that speed is 14.7 meters per second, and it's going to come to rest, instantaneous rest, at this point here at the top, and at that point the velocity is equal to 0. Now as soon as you've got three things, you can find the fourth, and we want to find s. So solve that again, SUVAT. I'm going to take upwards as positive, like this. S is what we're trying to find, so put question mark there. U, that's the 14.7 meters per second. V, that's going to be U, that's the point it becomes instantaneous rest. And A is going to be negative 9.8, so this is going down, and I'll leave T blank because I don't need to know T, I don't need to find T. So that equation we're going to use is V squared equals U squared plus 2AS. And we simply put our values in. 0 squared is equal to 14.7 squared plus, and we want to add 2 times by negative 9.8 S. So we'll rearrange it for S, and we'll have S is equal to 14.7 squared, it's going to be negative, divided by negative 2 times by negative 9.8, so negative 19.6. So if we work this out, we'll get S is equal to 11.025. Now if you wrote this down as your answer, you would lose a mark. When you use G, you must give your answer to 2 or 3 significant figures. Any more accurate than that and you'll lose an accuracy mark, because G is only given to 2 significant figures. So I will write S as 11.0, or you can write 11 to two significant figures, but do not give an exact answer when you're using G. And lastly, part C, how would this new value of the speed of the ball as it hits the ground for the first time compare with the value found using the initial model in part A? It would help if I read the bit before. In a refined model of the motion of the ball, the effect of air resistance is included, and this refined model is now used to find the speed of the ball as it hits the ground for the first time. How would this new value of the speed of the ball as it hits the ground for the first time compare with the value found with the initial model in part A? Well, air resistance slows things down. Things are going to move more slowly if we include air resistance. So our new speed will be lower than the value that we found in part A. So I'll just write that down. The new speed would be lower than in part A. So remember, air resistance slows things down. Question number 6. A car travels along a straight horizontal road between two sets of traffic lights. The distance between the two sets of traffic lights is 1,500 meters. In a model of the journey, the car leaves the first set of traffic lights, accelerating uniformly from rest until it reaches a speed of v meters per second. It then immediately decelerates uniformly until it comes to rest at a second set of traffic lights. The car completes the journey between the two sets of lights in 120 seconds. Part A, sketch on the diagram below, or the diagram over to the side here, a velocity time graph which represents the above model of the journey of the car between the two sets of traffic lights. Now, I don't know the rate at which it was accelerating and decelerating. Let's assume that it accelerates more slowly than it decelerates. We don't know that. All I know is that the line's going to go up to show acceleration and then go down to show deceleration in a time of 120 seconds. And then the highest point here is going to be a velocity of big V. As long as you've got a triangle here going up, going down with no straight line going across, because it doesn't stay at a constant speed, it accelerates and immediately decelerates. Got some sort of triangle, you get the mark. Part B, using the model, find the value of t. Now, I've been told in the question that the distance between the two sets of traffic lights is 1,500 meters. So the area here is 1,500. So I can use that in part B, so let's just label this as part A, to calculate the value of t, of v. So since it's a triangle, the base 120 times the height v, or half the base times the height, let's write that down. So half the base, so half 120 times the height v is equal to the area 1,500. So we just need to find v. Half of v is 60, so v is going to be 1,500 divided by 60, and that gives v as 25 meters per second. That's velocity there. Okay, moving on to part C. It is given that the car accelerates uniformly for t seconds, right? So let's put that in on our diagram. So this value here is t. Explain why there is a range of possible values for t which satisfy the requirements of the model. Now, the area of that triangle is fixed. Okay, so area of triangle is fixed at 1,500 because that's the distance travelled. Where the top of the triangle occurs doesn't make any difference to the area. So I could have a triangle that looks like this, going up like that and going across like that, it's still going to have the same area and the same height. So where T occurs has no effect on the area. So when T occurs, has no effect on the area. I'll finish it off by saying, so there are a range of values for T. And last bit here, part D, suggest one improvement, we only need one improvement, to the model that will make it more realistic. So here's a couple of example solutions we can have. So with the acceleration and deceleration phases, do it so that it's not uniform. It's unlikely that you have exactly uniform acceleration there. So actually variable acceleration, deceleration. And maybe include a section here in the middle where you have constant speed, because you know cars don't really accelerate and then decelerate straight away. They normally take their foot off the accelerator, they're moving at a constant speed for a little while, and then they slow down. Otherwise, literally what you're doing is accelerating and then immediately putting your foot on the brake. That doesn't really happen. So these are a couple of suggestions as what you could have for part D. Okay, question 7. A ball P of mass 0.4 kg rests on a rough horizontal table and is attached to one end of a thin rope. The rope passes over a pulley which is fixed at the edge of the table. So it's just fixed there. The other end of the rope is attached to a ball Q here of mass m kg which hangs freely below the pulley as shown in figure 1. The system is released from rest. Okay, so let's just highlight that, release from rest. The rope is taut and with Q at a height of 2 meters above the ground, that's marked in the diagram, and Q moves downwards with acceleration 2.5. Q moves downwards with acceleration 2.5 meters per second squared. In a subsequent motion, P does not reach the pulley before Q reaches the ground. So Q is going to hit the ground first before P hits the pulley. The balls are modelled as particles, the rope as a light and inextensible string, and the pulley as being small and smooth. The total resistance to motion of P is modelled as having constant magnitude 1.5 newtons. The acceleration due to gravity is modelled as being 10 meters per second. I'm going to highlight that because I don't want to be using 9.8. And what we need to do here, using the model, find to two significant figures. That's important, to two significant figures. Part A, the tension in the rope. So the first thing I'm going to do is to put on all the forces. So the weight of Q, mg, the tension going up, the tension pulling P, the resistance to P, which was 1.5 newtons. Let's stick 1.5 there. The directions they're moving in. Q is moving down with acceleration 2.5 meters per second squared. P is moving to the right with acceleration 2.5 meters per second squared. They have the same acceleration. Okay, so part A, tension in the rope. So to find the tension, I either need to write an equation of motion for Q or for P. If I do it for Q, I've got two unknowns, so I'm going to write an equation of motion for P that means that I'm going to be resolving horizontally. So that will be T minus 1.5, there's my resultant force, is equal to MA, 0.4A, and A is 2.5. If I solve that for T, so do 0.4 times 2.5 and add 1.5 to both sides, I'll get the tension as 2.5 newtons. Next, we'll find the value of M. Now, this is given to two significant figures, so I can leave it like that, don't need to write anything. So to find M, I'm going to do an equation of motion for Q. So resolve downwards, so that will be mg minus t, there's my resultant force, is equal to MA. So MA, A is 2.5. Now remembering that we use G as 10, so 10M, and then if I minus 2.5M, just rearrange it, is equal to T. Now T is 2.5. So I'll have 7.5M equals 2.5. So M will equal 2.5 divided by 7.5, which is a third, which is 0.333, and so on. We need to give our answer to two significant figures because of the value of G has been rounded to one significant figure. So 0.33, and that's kg. Right, moving on to part B. So we want to find the time after release for Q to hit the ground. So this is going to be a SUVAT question. SUVAT. I'm taking downwards as positive because that's the direction it's moving in. It's released from rest. So U is 0. It's 2 meters for it to hit the ground. V we're not interested in. A is going to be the acceleration of the particle, so not 10 but 2.5. The string is slowing it down, the rope is slowing it down, so A is 2.5, don't put 10 there. And we are trying to find the time, so I'll put a question mark there. So that's going to be S is equal to UT plus half AT squared. So 2 is equal to 0 times by T, 0T, plus half times 2.5 times T squared. So if we rearrange this to solve for T, so I'd get T squared first of all. That's going to be 2 divided by 1.25. That's 8 over 5, so that's basically 1.6. So T is going to equal the square root of that. So I don't want the exact answer. Remember, it says that I need to give answers to two significant figures. So 1.2649 and so on. So two significant figures, that will be T is equal to 1.3 seconds. And lastly, part C says here, state one limitation of the model that will affect the accuracy of your answer from part A. So I've given some suggestions for answers. It's just 1 mark, so you need to only give one. So air resistance, obviously that's going to slow things down, so that would change my answer. The pulley may not necessarily be smooth, we're assuming it's small and smooth, that has no effect on its motion. And the mass of the rope as well. Now if it was string, yeah, you know, we could probably ignore its mass, but because it's rope tends to be quite thick, doesn't it? So the mass of the rope, that's also going to affect the tension and the value of M. So these things are things that will affect the value of my answers in part A. Question 8. A particle P moves along a straight line such that at t seconds, where t is greater than or equal to 0, its velocity v is given by this. V is equal to 16 minus 3t squared. What we need to do in part A is find the distance travelled by P in the first second. Now, distance is basically that area under velocity time graph. So here's my velocity and here's the time. So the area is going to be given by integrating v with respect to t between the limits, in other words the time in the first second, so that's going to be from 0 to 1, and that will give me the distance. Let's call that s. So limits of 0 and 1, integrating 16 minus 3t squared dt. Let's integrate, so 16 becomes 16t. Negative 3t squared, well, you add 1 to the power and divide by the new power. So you'll have 3 divided by 3, So you'll end up with t cubed and limits of 0 and 1. We'll substitute those in. So I'll have 16 times 1 minus 1 cubed minus 16 times 0 minus 0 cubed. So obviously the second bracket is just 0, and then we've just got 16 minus 1, which is going to be 15 SI units, so 15 meters. That's part A. Part B. The value of t at the instant when p changes its direction of motion. Now, direction changes when v is equal to 0, because something is slowing down until it comes to instantaneous rest and then changes direction. So what we're going to do is to set v equal to 0. That means 16 minus 3t squared is equal to 0. That means we have 3t squared is equal to 16. T squared is equal to 16 over 3. So that will give me t is equal to 4 over root 3. Now it doesn't say how I need to give my answer. There's no values of g, so I can give an exact answer. Or if we whack this in our calculator, 4 divided by root 3, we can give a equivalent answer. So maybe 2.31 if we decide to give it to 3 significant figures. But in this question, an exact answer is not an issue. And then moving on to part C, what we need to do here, the value of t at the instant when p returns to its starting point. Now, something's going to return to its starting point when its displacement s is 0. So we need to find out an expression, first of all, for the displacement. That means integrating the velocity. That means integrating this expression. Now, we've already done that. S is equal to 16t minus t cubed. So I guess I could write here that S is what we get when we integrate v with respect to t. Now, when we integrate, there is a constant of integration here when we integrate without limits. Now, we can work out what the value of c is, because when t is 0, s is 0. So I think I am safe in assuming that this particle starts at the 0 position, because it does talk about returning to its starting point. So it's at its starting point, s is 0, t is 0, and when we substitute this in, we'll actually get a constant equal to 0. So we can forget about that. Here it's going to be 0 anyway. So it's now about setting this equal to 0. So we'll have 16t minus t cubed is equal to 0. So we want to factorize that to solve it. So we've got t, and then 16 minus t squared is equal to 0. So either t is equal to 0, well, that's when s is 0, we know about that, or it's when 16 is minus t squared is equal to 0. In other words, let's do it over here. T squared equals 16. So t is plus or minus 4, but time can't be negative. So t is 4. So 4 seconds is going to be the point when it returns to its starting position.